Hi everyone. So now we're going to talk a little bit about how we use the definition of the Laplace transform to develop some of its properties when the Laplace transform exists, and then how we actually approach solving differential equations with the Laplace transform. So we're not going to spend a lot of time on the existence theorem proving it, but you should at least know what sort of functions are guaranteed to have Laplace transforms. And this is not an exhaustive list. There are functions that are not included in this class that also have Laplace transforms, but this gives us a basis of functions to work with that is pretty much everything that you're going to see in practice. So I mentioned before that if you're looking at an integral like the integral from 0 to infinity of f of t e to the minus st dt, and you want to know when this integral exists, when this converges, then what we need is for f not to grow as quickly as e to the minus st collapses. And a way that we can guarantee that happens is we define what it means for a function to be of exponential order. So we say f is of exponential order if the absolute value of f of t is less than or equal to m times e to the at for some constants, m and a. What that means is that f can be completely contained underneath some exponential multiplied by some amplitude increasing factor. So this is pretty easy to show for basic functions. For example, the cosine of x. Well, since cosine of x looks like this, it's pretty obvious that from 0 to infinity, cosine of x is just trapped underneath e to the x. So in this case, m would be equal to 1 and a would be equal to 1, and then we can just say that the cosine of x in absolute value is always underneath e to the x. And so cosine of x is of exponential order. Okay. Similar rules apply to things like polynomials. So, for example, x squared is of exponential order, because exponentials grow faster than polynomials for any power of a polynomial. You have x squared looks like this. Okay, that's growing pretty quickly because it's a parabola. But if you just put e to the x in here, e to the x is always bigger than x squared. So since e to the x is always larger than x squared, say in absolute value, which is kind of a meaningless statement because x squared is positive, then x squared is of exponential order. And more generally, x to the n is of exponential order for any n. Okay? And then any fixed exponential is of exponential order as well. So if I had something like e to the t, well, e to the t in absolute value is certainly less than, say, e to the 2t. So any exponential function is of exponential order as well. So the functions that are of exponential order include all the exponentials, all the polynomials, the logarithms, and all the trig functions. So we can define the family of functions that is of exponential order in the following way. So E0 infinity is the family of functions of exponential order that are piecewise continuous. So not even continuous, but piecewise continuous. So as long as I can break it up to an at most countable number of continuous pieces, then those functions are just in this family E of 0 infinity. And the theorem that tells us that pretty much everything we're going to encounter in practice has a Laplace transform is that, so this is the big theorem here. We're not going to prove it, we're just going to assert it, that every f inside the family of functions of exponential order on 0 infinity has a Laplace transform. And then remember that the big deal here is that things like all the polynomials, cosine, sine, and all of the exponentials all live inside this family E0 infinity. So the basic functions that we come across in almost every application are of exponential order. And that means they all have Laplace transforms. I should point out that that doesn't mean that this is all of the functions that have Laplace transform, because there are functions that are not in this family that do have Laplace transforms. For example, 1 over the square root of t has a Laplace transform, but 1 over the square root of t is not of exponential order. The upshot of the theorem is that the elementary functions of calculus have Laplace transforms. And that also means that the elementary functions of physical modeling have Laplace transforms as well. Since we want to use the Laplace transform to solve problems by applying the Laplace transform, solving it in the Laplace domain, and then finding an answer that corresponds to that answer in the original setting, we're going to need a way to come back from the Laplace transform. So we want to define an inverse Laplace transform. And we can do it in the following way. So now this is going to seem like kind of a cop-out, the way I'm going to define this, but this is the same way that when we defined antiderivatives for the first time, that we defined antiderivatives. So we're going to say that a function has an inverse Laplace transform if it is the Laplace transform of some function. So L inverse of f of s is said to be equal to f of t if and only if the forward Laplace transform of f of t is equal to f of s. This is exactly the same as the way we set up integration and differentiation at the very beginning. A function is called an antiderivative if its derivative is the original function. A function has an inverse Laplace transform if it is the Laplace transform of that function. Now, it's possible to define the inverse Laplace transform in terms of an integral, just like we define the Laplace transform in terms of an integral, but it's an integral defined in terms of complex numbers, and we hardly ever work with it. We just work with pairs of functions where we already know what the Laplace transforms are. So what that means is every Laplace transform induces an inverse Laplace transform. So if I start writing down rules for Laplace transforms, I'm also writing down rules for their inverses. We've already shown that the Laplace transform of 1 is equal to 1 over s. And that means that the inverse Laplace transform of 1 over s is equal to 1. We've already shown that the Laplace transform of t is 1 over s squared. And that means that the inverse Laplace transform of 1 over s squared is t. We've already shown that the Laplace transform, we haven't shown this, but we've asserted that the Laplace transform of t to the n is equal to n factorial over s to the n plus 1. And that's going to induce the inverse Laplace transform that the inverse Laplace transform of s to the n plus 1 is equal to 1 over n factorial t to the n. Okay? So for every function that we have on this list, every time we compute a Laplace transform, we automatically get an inverse Laplace transform relationship for free. You can also find Laplace transforms of sines and cosines. It's a very common thing to do. So the Laplace transform of the cosine of bt is equal to s over s squared plus b squared. And so, of course, that means that the inverse Laplace transform of s over s squared plus b squared is the cosine. So a similar rule holds for sine. The inverse Laplace transform of, the Laplace transform of b over, the Laplace transform of the sine of bt is equal to b over s squared plus b squared. And so the inverse Laplace transform of b over s squared plus b squared is sine of bt. And so that body of knowledge, our basic Laplace transform patterns, that's going to be the sort of launching point that we're going to use to start studying equations. Before we do that, though, we should look at how to do inverse Laplace transforms of some example functions. And we're going to use the fact that the Laplace transform is linear to do that. So here's example 1. Let's compute the inverse Laplace transform of 2 over s squared. So linearity says that this is equal to 2 times the inverse Laplace transform of 1 over s squared. But I know what the inverse Laplace transform of 1 over s squared is. It's 1 over 1 factorial times t to the first, which is 2t. The inverse Laplace transform of 3s over s squared plus 4, I think to myself, s over s squared plus 4 is very much like a cosine, where the b was equal to 2, except there's that 3 in there. So what I can do is I can pull the 3 out. Now I'm looking at the inverse Laplace transform of a pattern I know. S over s squared plus 4, that's right here, because 4 is equal to 2 squared. So this is equal to 3 times the cosine of 2t, because I recognize that pattern from the table. A more typical problem might ask us to find the inverse Laplace transform of several of these patterns stuck together. And our task is going to be to unwind the function into something where we recognize what the patterns are so we can go backwards. The typical tool that's used to do this is partial fractions. Suppose I was asked to find the inverse Laplace transform of something like 3s plus 2 over s minus 1 times s minus 2. So this is a pattern that's not obvious. If I had s squared on the bottom plus b squared, so that is no s terms, then I could think of this as sines and cosines. The problem is I've got those s terms running around in the downstairs. If the s minus 1 and the s minus 2 were by themselves, then I could use the fact that I know that the Laplace transform of e to the at is equal to 1 over s minus a, which means the inverse Laplace transform of 1 over s minus a is equal to e to the at. The problem is that they're stuck together as a product, and this is where partial fractions come into play. What I can do is I can rewrite 3s plus 2 over s minus 1 times s minus 2 in partial fraction form. And partial fractions are going to be a core technique in what we're doing here. Okay, so if that's the sort of thing you haven't paid attention to in a while, you're going to need to pay attention to it. So with a little bit of elbow grease, I think you can figure out, if you put in the 1, you get 5. So this is, I think, minus 5 over s minus 1 plus 8 over s minus 2. And that's your partial fraction step to get you there. But just like in integration, the partial fraction step is just a tool that you're using to get to a function that you can actually do something with. So we're going to take the inverse Laplace transform of this form of that function. So this is the inverse Laplace transform of minus 5 over s minus 1 plus the inverse Laplace transform of 8 over s minus 2. And using this formula, that means that this must be minus 5 e to the t plus 8 e to the 2t. And that's typical of these type of exercises. We get a complicated function that's a rational function. We break it apart into pieces, and then we analyze those pieces separately. And the breaking apart step is a partial fraction step. So that's typical of the approach that we're going to take to these problems. Finding an inverse Laplace transform is all about finding a pattern that you recognize from a table or a list of known transforms. Now, what does the actual inverse Laplace transform look like? Well, L of f is equal to the integral from 0 to infinity of f e to the minus st dt. That's great. Why don't we write the inverse down in terms of an integral? After all, in the Fourier transform, both the Fourier transform and its inverse were integral formulas. We might expect that the inverse transform here has an integral from 0 to infinity, and maybe not an e to the minus st, but an e to the positive st. And that's true. It's just that the integral that you have to use is in the complex plane, and it's not. And the technique that you use to evaluate it is one of the central techniques of complex analysis. So the actual definition of the inverse Laplace transform of a function f of s is that you take 1 over 2 pi I, and then you take a limit as t goes to infinity, and you take this integral in the complex plane, some number, say a, plus, so from a minus it to a plus it of capital F of s e to the positive st dt, where a has to be larger than all of the singular points of f of s, and f of s is bounded. That's kind of ridiculous. If you want a picture of what's actually going on here, f of s is going to have some poles, right? Some singular points inside of it. Because remember, we're expecting f of s to be rational. So what you do is you pick an a that's out here past where all those singular points are, and then you look at the line, this vertical line that goes from a plus it to a minus it, and then you evaluate the integral on that line in the complex plane. So you have to evaluate the integral and then take this limit, and there is your inverse Laplace transform. So it's just easier to define the inverse Laplace transform for us as the function that exactly corresponds to the forward direction of the Laplace transform. But if you're curious about why we're not actually doing it from the integral, this is why. So we actually don't know how to integrate this unless we learn what's called contour integration in the context of complex analysis. So that's supposed to be an argument for potentially thinking that you should take complex analysis at some point. So now, armed with our basic table of Laplace transforms and their inverses, and with the knowledge that the Laplace transform of a derivative has a very nice formula, we're actually ready to start using the Laplace transform for its major application, which is the solution of ordinary differential equations that have initial conditions. So beyond the rules for Laplace transforms and their inverses that we wrote down earlier, the one thing from the last lecture that we're going to need is the formula for the derivative of a function. So if I take the Laplace transform of a derivative, remember that what we got out of this was s times the Laplace transform of the function minus the initial value of the function. It's more common to write this as s times capital Y of s minus lowercase y of 0, so that you're not having to write L's all over when you're plugging these things into equations. Okay, so that's a rule for transforming derivatives. Remember that L of y, we're always thinking of being capital Y of s. We'll come up with a rule for the second derivative when we do the second example here. But this, combined with our knowledge of the basic Laplace transforms, is enough to solve a very simple initial value problem. So we're going to solve this. dy dt is equal to t, and y of 0 is equal to 1. Now granted, this is not a very difficult problem. You can just integrate both sides. And what you're going to get is that, so if you integrated this, you would get y is equal to 1/2 of t squared plus 1. That's what you get after you apply the initial condition. So you integrate, you get a plus c, you solve for it by plugging in the initial condition. Of course, we have this super high level tool, so let's use it to crush this problem. So what if we did this with the Laplace transform? Because that's going to be illustrative of the way that these problems are going to tend to go in the Laplace transform. Y prime is equal to t, and y of 0 is equal to 1. So I'm going to apply the Laplace transform to both sides. The Laplace transform of y prime is equal to the Laplace transform of t. And I know how to evaluate that. The Laplace transform of y prime is s, capital Y of s, minus y of 0. And the Laplace transform of t, I can read off the table. That's equal to 1 over s squared. Now I also know y of 0 because it was given to me. So this equation is actually sy of s minus 1 is equal to 1 over s squared. Now the game is, I've taken this differential equation and I've turned it into an algebraic equation. This thing that I've got here, I can solve for y. And so I'm going to do that. Y of s is equal to 1 plus 1 over s squared, all divided by s. And that means that y of s is equal to 1 over s plus 1 over s to the third. So I've solved the differential equation in the Laplace domain. But the goal is to try to take this function and move it back into the time domain. So I have to take an inverse Laplace transform. Y of t will be the inverse Laplace transform of 1 over s plus the inverse Laplace transform of 1 over s to the third. Well, the inverse Laplace transform of 1 over s is 1. And the inverse Laplace transform of 1 over s to the third is 1 over 2 factorial t squared, which is 1/2 t squared plus 1. So yes, we've sort of smashed this very simple problem to death with this enormously high-powered technique, but the idea of how we went through the application of this is going to work even in more complicated problems. The whole point is to reduce the original equation so that I have an algebraic equation where I can isolate this y of s. And I'm going to get some mess on the other side like this, and when I come back, I'm going to have it broken up into patterns that I recognize. So let's do another example. So the next example that we're going to work on is going to be a second order equation. And so we're going to need to know how to do the Laplace transform of the second derivative. So the Laplace transform of y prime prime turns out to be s squared y of s minus s y of 0 minus y prime of 0. Okay. It's got the same structure as it does in the first derivative case. And the reason that we get this trailing chunk of things poking out the side, the y of 0 and the y prime of 0, is just the result of integration by parts. So we'll leave it as an exercise to show what the rule is for a general nth derivative, but the same kind of pattern holds. Okay. All right. So that's all we need to solve a second order equation. And so let's write one down. Y prime prime minus y prime minus 6y is equal to 0, with the initial conditions y of 0 is 1 and y prime of 0 is 2. So how would you solve this equation using the techniques that you know from Math 244? Well, this is a differential equation with constant coefficients, and it's linear second order. And so the method you would have used prior would be the characteristic equation. So you would solve the characteristic equation for the homogeneous solution. That would have been m squared minus m minus 6 is equal to 0. You factor to find the factors of m minus 3m plus 2. So m is 3 and m is negative 2. And that means that you know that your homogeneous solution was equal to c1 e to the 3t plus c2 e to the minus 2t. And now you've got to apply the initial conditions and you get a system of equations. You solve for c1 and c2 by grinding, right? You get c1 and c2 by plugging in and grinding. So the Laplace transform is going to make this much more elegant. And the reason is I actually don't have to plug in to find the c1 and the c2. Because this transform right here includes the initial conditions are already going to be built into the answer that comes out, which is pretty elegant. So let's do the same problem, but let's do it with the Laplace transform. Okay, so we Laplace transform both sides. Should be no surprise that the Laplace transform of 0 is 0 because you're just integrating 0. So what do we get? Oh, I should write down here the initial conditions. Y of 0 is 1. Y prime of 0 is 2. So the Laplace transform of the second derivative is s squared y of s minus s times y of 0 minus y prime of 0 minus y prime, which is s y of s minus y of 0 minus 6 times the Laplace transform of y, which is just y of s, and that's all equal to 0. This is an algebraic equation because there's just y of s's running around all over the place, and so that's what I'm going to isolate. The first step I can do to do that is to write this. And notice that the equation that's in here, the little chunk that's in there, that is the characteristic equation of the system. So the Laplace transform is encoding the characteristic equation. So those roots are going to come into play. Now, this stuff over here is going to be a problem because it's on the wrong side. I need to isolate y. So I'm going to rewrite this as s squared minus s minus 6 y of s is equal to s plus 1. And now dividing both sides by the polynomial on the left gets us y of s is equal to s plus 1 over s squared minus s squared minus s minus 6. Oh no, I don't recognize what to do. So I'm going to have to take this thing and break it up using partial fractions. So I have now solved the problem. This is solved in the Laplace domain. That's the answer. In fact, in a lot of engineering and science applications, it's enough to just stop here. You have a characterization of this system in the Laplace domain, you can just study it over here. If you want to implement something about that, though, you have to go back to the time domain. So if y of s is equal to s plus 1 over s squared minus s minus 6, then remembering our partial fraction theory, let's see, which I'm sure everyone in here is a complete master of. S plus 1 over s minus 3 times s plus 2 is a over s minus 3 plus b over s plus 2. Pick your favorite method for finding a and b. I believe what you come out with in this case is that this is equal to 4/5 of a 1 over s minus 3 and 1/5 of a 1 over s plus 2. So using your partial fraction step to go from here to here, y of s is equal to 4/5 1 over s minus 3 and 1/5 1 over s plus 2. And now these I do know the inverse Laplace transform of because these things correspond to the Laplace transform of exponentials. The rule that's operating in the background here is that the Laplace transform of e to the at is equal to 1 over s minus a. So that means that y of t is equal to 4/5 of e to the 3t plus 1/5 e to the minus 2t. And notice here, there are no constants left. All the arbitrary constants have been solved for because the initial conditions are already encoded into this process, which I think is kind of an advantage over using the homogeneous equation then solve for the constants technique. All right, so for our last example, we're going to look at a slightly more complicated problem that has a forcing function. So let's look at y prime prime plus y is equal to e to the 2t, where y of 0 is equal to 0, and y prime of 0 is equal to 1. So we take the Laplace transform of both sides. What do we get? So we're going to get the Laplace transform of y prime prime plus the Laplace transform of y is equal to the Laplace transform of e to the 2t. Doing those transforms gets us s squared y of s minus s times 0 minus 1, because that's y of 0 and y of 1, plus y of s is equal to, okay, the Laplace transform of e to the 2t. I consult my table. It will show me that this is 1 over s minus 2. Okay, so let's do some algebra to isolate ys. Ys times, let's see, what do we get? An s squared, and then there's a plus 1 And what's left over is, well, 0 times s is just nothing. And then there's this -1 floating around. Okay. So y of s is going to turn out to be equal to 1 over s squared plus 1 times 1 plus 1 over s minus 2, which if you combine the fractions together and then multiply through by 1 over s squared plus 2 plus 1, I think you get s plus s minus 1 over s squared plus 1 times s minus 2. Well, I've solved the problem, right? As long as I restrict my attention to the Laplace domain, I'm done. Except that's not usually the way it works. I want to know what's happening in the time domain. What's the solution to the original differential equation in the time domain? Fortunately, I'm a master of partial fractions, and I know that this must be equal to as plus b over s squared plus 1 plus c over s minus 2. Now, if you go through the work, this is going to turn out to be equal to 1/5 of 1 over s minus 2, and then minus 1/5 times s minus 3 over s squared plus 1. And I should split it one step further, because this term right here, this doesn't mean anything at this point, because I don't know what that pattern is. If it was s over s squared plus 1, it would be a cosine. If it was 1 over s squared plus 1, it would be the Laplace transform of a sine. But it's neither right now because there's a whole s minus 3 up here. So I need to go one step further in breaking that up. This is 1/5 times 1 over s minus 2 minus 1/5 times s over s squared plus 1 minus, I guess, plus 3/5 times 1 over s squared plus 1. And the point is that this is a table transform, this is a table transform, and that is a table transform. Those are the sort of patterns that you should be aiming to memorize, the basic ones. Because now y of t is 1/5 e to the 2t minus 1/5 cosine of t plus 3/5 of a sine of t. So if you know the patterns, then when you do the inverse Laplace transform and you recognize those patterns, it's very easy to come back from the table to the time domain function that corresponds to the transform. So what are the difficulties going to be in solving these problems? Like, what's the core difficulty? The technique itself is actually pretty easy. What do? We just took the differential equation, we apply the Laplace transform, we have formulas for computing all these bits. That's easy. Now, I did know that the function I stuck over here, this e to the 2t, I knew how to do that because that was on the table. And then the algebra is easy step. This algebra is an easy step, but recognizing functions that I know the transform of, that's a hard step. So there's two hard steps here. The first hard step is knowing enough of these to be able to compute these without having to grind out some terrible integral. And the second hard step is knowing enough of these to recognize transforms of functions. And so really what we need is a giant pile of transforms where we can just work with them. We know what the functions are, we know what their transforms are, and it's very easy to go back and forth. So the hardest thing here is having lots of known transforms. Ideally, we'd be able to work with all kinds of combinations of polynomials, exponentials, and trig functions. Because those are the sorts of things that come up when we're doing ordinary differential equations. The other type of functions that we're going to, sort of our longer term goals, would be step functions, which act like switches. That'd be a great goal to have. These are sometimes called Heaviside functions. And impulse functions. So an impulse function is a function that just instantaneously imputes force into a physical system. So an impulse function is sometimes called a delta function. A Dirac function. Okay, so here we've got Heaviside is the name associated with these, and Dirac is the name associated with these. Those are also goals that we'd like to have, because in modeling with systems, I would like to be able to deal with functions in a physical system that turn off and on or change their behavior, and I can do that with step functions. Or systems where I can shock the system by putting an impulse. In fact, impulse response is the core way of analyzing what the basic behavior of a system is. So the delta functions turn out to be incredibly important. If you've never seen a delta function before, don't worry about it, because we're going to do it in detail. But the basic idea of a delta function is that it allows an instantaneous application of force to a system. All right. So the big idea of what we just did was an approach to solving differential equations. And it's always the same. We start with an ODE. We transform it from a differential equation into an algebraic equation using the Laplace transform. Then we solve it algebraically for y of s. And once we've done that, we have to come backwards with the inverse Laplace transform to get the solution to the ODE. Okay? And that is going to be basically our approach to all of these differential equation type setups. Where we need to work is on being able to find lots of functions that we can use in the original ODEs. I want a full set of functions that I understand for using in an ordinary differential equation. And then I have to be able to do this step where I can recognize what the solutions look like in terms of being the transforms of known functions. And so the art in using the Laplace transform is in this step right here at the bottom, where I go back and I have to recognize the patterns. So work hard on these. I actually think this is a really fun way of solving differential equations, especially because it already includes the layer where prior to this, maybe you have to solve for the arbitrary constants. You've got to do things like the method of undetermined coefficients. That's all just built in here. All right. See you next time.